Hello. In this video, we are going to work on differential equations. I'll often abbreviate that diffie-Qs. We're going to talk about two ways to solve them, or to figure out what solutions would act like, I guess we can say. One is called separation of variables. That gives us an equation for the solution. And the other one is called slope fields. And slope fields gives us a graph that tells us what the solutions would look like. So the first thing that we're going to do is talk about what a differential equation actually is. And it's a pretty simple definition. A differential equation is just an equation that has derivatives in it. It can have all kinds of derivatives in it, and there are actually like multiple different courses in math about how to solve different types of differential equations. And here in this class, we're just going to focus on ones that are solvable by a particular couple solution methods. So these are three examples. First one, dy dx equals x squared. This could also be written as y prime equals x squared. And if we're assuming that the derivative of y is with respect to x right here, then these two are representative of the same thing. Down here, I have dy dx equals x times y squared. And down here, I have dy dx equals 2x. Now, you can already solve two of these without any of the new methods. So take a look at this and see which ones you think you can solve using just basic integration methods from the class so far, and then figure out which one you don't know how to solve yet. All right, so hopefully you said, all right, I can solve this one and this one. This one at the bottom is actually, well, they're both simple power rule, but you can integrate both sides here. And if I integrate the left side, I get y. And if I integrate the right side, I get 1/3 x cubed plus a c. So that would be the solution to example number 1. And then for example number 3, see if you can figure out the solution. Take a look at it right now. Okay, hopefully you said, all right, I integrate the left side, I get y. I integrate the right side, I get x squared plus a constant. So when we talk about differential equations, we can talk about solutions to differential equations. So this right here is the general solution to that differential equation. It's general because it has this plus c. If I've solved for a c, which is something that we've done in this class, then I have a particular solution. So say for example, I had the parabola x squared plus 8. That would be a particular solution to this differential equation. Y equals x squared plus c is the general one because it contains all particular solutions. Sort of defined a differential equation. We haven't talked about separation variables with that soon, but I'm going to talk about slope fields. And in order to do that, I am going to use this differential equation right here. All right, so this is a slope field generator that I found on Desmos, and I'll include a link to it in the description. But take a look at it. It says g of xy is 2x. So that's the equation that we had previously on that other page. And then that is dy dx. And it has all this Desmos stuff that creates the slope field. So let me show you what the slope field is. What the slope field is it gives me a little line that tells me, it's kind of like a mini tangent line at any given point. So you can see I can move this thing around, and it changes to match all of those pieces. Now what I'm going to do is graph y equals x squared, and I think that'll help you see what all these lines are. So we know that the solution to this would be x squared plus c. If I had c equals 0, it would be this thing. So look, do you see that right here? It's almost parallel to that right there. So in this spot right here that actually goes through, we can't even really see that little slope field piece because it is parallel to this line, or to this parabola right here. So what the slope field does is it kind of tells us different spots that would it tells us the direction of the solution at any given spot. So you can see I can add in more pieces, and all of them will fit. Look, everything has a slope of 0 at x equals 0, so it's flat here. So all these parabolas that I'm going to put in here are flat. So what the slope field does is it gives us a way to visualize what all the solutions would look like. So I could not have any of these here, and I could say, oh, any solution. It's going to start, it's going to go down, it's going to flatten out, and then it's going to go back up. So for some equations, we can actually solve them, and doing things like slope fields is the only way to get an idea of what they look like. All right, so right here, what we're going to do is actually create part of a slope field. It can get really long to create one like the one you just saw on the graph over there, but usually when you're asked to do it by hand, there aren't that many pieces that you need to work on. So notice that this has dy dx equals x times y. So what we're going to do is evaluate dy dx at each of these different points here. So notice we have 0, 0, 1, 0, 2, 0, you know, this is 1, 1, this is 2, 2, this is 2, 1. You should be able to get all those points, and then you can evaluate this thing. So let's do it at 0, comma 0. That is going to be 0 times 0, which is just 0. So what I can do is just draw a little line like that. And we like to take shortcuts when we can. So when I do this, I'm like, oh, 0 times 0, 0. Well, look, if x is 0, or if y is 0, then dy dx is 0. So I can just draw a slope of 0 at all the spots where x and y are 0. And now I cut that, actually close to cut my work in half, right? So let's go ahead and do this point right here. What are the coordinates there? Dy dx evaluated at 1, comma 1. Well, that would be 1 times 1, which is 1. So it has a slope like this. What I'm drawing it there as is, I'm drawing it as if it were to hit this point here and this point here. That's how I kind of calculate that slope of 1. So I'll get rid of that piece. All right, so let's do dy dx evaluated at this point right here. What are the coordinates there? It's 2, comma 1. What's that? It's 2 times 1, which is 2. So here, what I can do is draw a line that would go through here, and then if it were to continue out far enough, it would hit this, because that's a slope of 2. So I just draw that. Come up here. I think you should see that that calculation is going to give me 1 times 2. So that goes like this. This one is going to give me, well, that's 2, comma 2. So 2 times 2 would give me a slope of 4. So that would go, it would go from here to there. And I'm just going to draw like that, and then erase this little thing here. You might be able to see that, like, once we get to like 4 on a slope, like it gets so steep that they all sort of look the same. So back here, this one's going to be negative. Whoops, I'm on an eraser. Let's go to this. This is going to be -1, and this is going to be -2. And you could do those calculations. So hopefully you see how to do a slope field. And now we're going to do some matching problems. All right, so here we have four graphs and 4 equations, and I want you to try to match them. So which one goes with this, which one goes with this, which one goes with this, and which one goes with this. I'd like you to look at, spots where the slope is 0, or regions where the slope is positive or negative, and that tends to be the best way to figure out. So go ahead and hit pause, see if you can do it on your own, and then we will do it together. Okay, here come the answers. All right, so what I'm going to do is kind of use a process of elimination. This one is going to be B, and let me explain why. Take a look at this equation. It's 0.5 times y. So first thing, it's only dependent, the slope is only dependent on y. That means that if you change x, that the slope is not going to change. So notice if I were to pick this row where we have black lines, if I move side to side, the slope does not change. That would be changing the x, and the slope doesn't change. Secondly, notice up here, all the slopes are positive, and up here, all the slopes are negative. So if y is positive, slope is going to be positive. Y is negative, slope is going to be negative. So this one fits that right there. And if I look at all these others, there are none of them that actually fit that property where all positive, all negative, above and below. So B has to be that one right there. The next one that I'm going to go after is this one. I look at this one right here, and I see that when x is equal to 2, because it may be really hard to see, but there's a tiny little 5 right there. But when x is equal to 2, the slope is 0. And that's true all the way up and down, no matter the y. If you look at that, if I plug in 2, nope, doesn't go to 0. 2, nope, for x doesn't go to 0. We already did this one. Look, if I plug in 2 for x here, then I get 0.5 times 2 minus 1, which is 0. So I think this one should be A. And notice it is the solutions here. If I were to draw a solution in, like this, they would be parabolic. And if I were to, this is one that we could actually integrate. And if I do the integral of that, I would get a parabola. I would get an x squared equation. I think I would have maybe a 1/4 out front or something like that. But it fits, right? There's nothing else for which the derivative would be 2 everywhere, so it's got to be that one there. All right, so the next one, this one's a little funky, so I'm going to kind of wait for that one till the end. Now I want to figure out which one has to be this. So what I want you to see is that in quadrant 1, all the slopes are negative. In quadrant 2, and maybe I could write dy dx instead of m, dy dx is equal to positive, right? All of these are going up. Even though like it's close to flat, it's still going up. And then here they're all negative, and then here they're all positive. So what we should recognize is that for this slope field right here, if x and y are both positive, then the slope should be negative, right? So if I put a positive x and a positive y in here, that doesn't fit this over here, right? I can't get a negative out if I do a positive plus a positive. So let's look at C. If I do a positive here and a positive there, then I do get a negative slope. And then that pattern will fit for all of these other ones. For example, let's come over here. Quadrant 2, that would be x negative and y equals positive. And if you plug that in here, then I get a positive slope. Similarly, look at this. I got a slope of -1, -1, -1, -1, -1, -1, -1. So the slope appears to be -1 as we go out along the line y equal x. Notice if x and y are the same thing, which is what we would get along that line, I get a slope of -1. So this one's C. And this last one has to be D. I could go into a longer explanation of that, but for the sake of what I'm doing right now, I think that I've got my point across in terms of like this matching stuff and what we look for. We look for where things are positives and negatives. So the last thing that I want you to do, and what we're going to do is focus on this equation right here. It's dy dx equals -x over y. What I'm going to use it to do is to demonstrate what separation of variables is. I think you should hopefully have like a little bit of an understanding of what a slope field is and how to start to generate it. And I think you hopefully can see why this thing matches this right here. What I want to point out before we do our separation of variables is that if I were to draw solution curves in, we get circles. And that goes for, any set of solution curves or something that looks like it's a circle. And I guess I should make one more point here. So this doesn't do it, but a lot of times when we have, if I were to do dy dx right above, evaluated at y equals 0, I would get -x over 0. And that doesn't exist. But we do know that it goes to infinity. And that actually matches this graph over here because y equals 0 is the x-axis. So we would get little vertical slopes if the Desmos could graph them, but Desmos, when it tries to plug in that 0, gets a DNE, so it doesn't graph it. So those vertical slopes actually match these circles. So in the next video, I am going to use this to show separation of variables, and we are going to connect it